Okay, before we go ahead and take a look at this battery, I needed to clarify something from video number 8. When we're operating in coherence mode, I had the question asked of me, does that impact the charge rate of the battery? And yes, indeed it does. When you have a CEC, which is at a somewhat fixed rate, this is not an infinite CEC. This does have a fixed value to it. And if we take energy away from the charging electrodes internally in that structure and we apply it back to the exciter to sustain its operation, yes, we are pulling charge current away from that battery. To what extent you can increase the CEC if you don't want to bother with charging a battery, that more or less is open-ended to an extent. Again, there are limitations to everything, obviously, but the simple answer to the question is, when we are in CEC greater than 1, do we pull some of the available energy that we could be using to charge that battery? And that is correct. That does happen. So let me take a look here before we get going. Take a look at this cell. You can see the production. And as we left it in the last video, we're showing no current plus or minus 2. So I only have 2 hands, and what I'm going to do is I'll go ahead and stop the video. You're going to have to trust me that I'm putting the right battery up here, but I'm going to take and pull the battery out of here and hook it up to the analyzer, and we'll move on from there. Right now the battery's reading 1.290. So we'll go ahead and hook it up to the analyzer and I'll be ready. Okay, what I've done here is I have removed that battery. I've connected it to the analyzer, as you can see here, with this very ingenious configuration, which I have no idea who to credit this to, but where we use a couple of small magnets on each end of the battery to the clips. I find that was a very ingenious way of making temporary working connections. Now I'm going to turn this light out. We don't need it. Okay, so now it read 1.29. You can see when we took it off of the cell, and right now this unit is saying that it's dropping. It's 1.277 at this time. Let me go up and set this up for a load of 7 milliamps, which will be in the area of about 0.1 C, or 1% of the battery's capacity. So we're going to draw a constant current of 7 milliamps off of this battery, and we're going to see, I'll go ahead and even set a timer down here. Normally I do this on a computer so it will draw a graph and keep all the values. We can figure rates and everything. But I'll go ahead and try to start this timer about the same time I take and start this unit up. I'll start the timer right now. It's at 0. We'll go ahead and turn it on, start the timer. And as you see, we are discharging the battery now at a rate, upper left-hand corner, of 7 mils. That's what we set up as our constant current. And you can see the battery voltage going down as we're dropping, as we're pulling the 7 mils out of there. Now, obviously this was not a phantom or a ghost voltage. We did actually put charge into this NiCad, and I'm quite surprised at how well it's actually doing considering the starting voltage. I'm sure we had dendrites and all kinds of damage internally to that battery, but for some reason it seems to be holding up quite well. I'm very surprised at that. I can tell you though, from experience, from watching the rate of discharge, that it did not take a full charge. In other words, the efficiency of the battery. Even though we're approaching full charge voltage, we have not put the amount of current in there that we normally would in a conditioned NiCad battery. Now, I'm sure that most of you should be familiar with the idiosyncrasies of NiCad batteries, their memory problem, and the fact that they like to be fully discharged. They like to be discharged at a high rate. Charging, if you want to extend that battery life past what they normally tell you can use, use a good old, somewhat expensive burp charger. You can get a very extensive use out of that battery if you properly take care of it. But anyway, we can see here that we're pulling that 7 mils out of there. The voltage is going down, and I'm not going to sit here on the camera all the time that we discharge this thing, but we're 2 minutes into it, and you can more or less get an idea of what's going on here. And you can see that this particular metering circuit drops at 2 thousandths at a time in reading. It doesn't go an individual thousandths. But anyway, I think I proved the point. That was not a ghost voltage. I am not attempting to prove the fact that that battery is in beautiful condition, because it definitely is not. It was not, and I knew it. And I just wanted to see what we could actually do here. And I'm very, very surprised at it, although you can see we're starting to drop more rapidly now. We should shut this off. The NiCads really don't like to go below 1.1. If you take them below 1.1, about the only time you should do that is if you're doing a rapid discharge and conditioning. A lot of the new burp chargers, which I say are very expensive, not very, but quite expensive, the burp chargers, some of them have a built-in discharge circuit so that you can cycle them properly. But I'm not going to take this guy down anymore. Let's see what happens when we take and turn it off. And lo and behold, that battery is going to recover. Now, I did not expect that. Okay, well enough. Well, we did charge that battery. We started out at about 0.044. It was in horrible condition. I'm sure it's still in very bad condition, although surprisingly enough it did quite well. And we were into it for probably about 2.5 minutes. And so it was not a ghost or phantom charge. We were charging it from this arrangement for sure. And of course you can see now that the cell is dead because we've removed the power from it. We need a potential to keep it in operation. Okay, we'll move on to a capacitor and take a look at that. For many of you, you have this hang up that you want to see capacitors versus batteries, and we'll go ahead and move in that direction.